Hi everybody, welcome to another video in Discrete Math, section 2.4, sequence and summations. So sequence, the way we define sequence is just like a function, except the domain will be whole numbers, or could be natural numbers. Alright, so here's some introduction there, but we define a sequence is a function from a subset of integers, usually either a set of whole numbers or natural numbers. The difference between the sequence and the function is that the way we write that, we use the subscript instead of a number in the parentheses. For example, if we write a sub n as n squared for the function, we write x squared. We say, what's the big deal, right? The big deal is the just notation first, it's a subscript. And it's inside the parentheses like that. Right, number one. Number two, there's no problem if we want to evaluate f of 0.5. But in the sequence, we don't have that. It have to be of the whole numbers or zero. We don't usually use negative either. Right? Now, next, let's look at this example. Find the first four terms of the sequence. In that case, well, that's easy enough. N greater than or equal to 1, so we say from n equal to 1, we have the first term, n equal to 1, sorry. A1, just put 1 over 1, so it's 1. N equal to 2, A2 equal to 1 over 2. N equal to 3, A3, N equal to 4, A4. So, pretty much that. Just like a function, except we use the whole numbers and then we put at the subscript. Right, next, find the next three terms of the following sequence. So this example, we should see the parent. So how do we get from this to the next? And here we say 1, 3, 5, 7. It looks like we're going to add 2 every time, right? So the next would be plus 2 would be 9. Plus 2 again would be 11. Plus 2 again, that would be 13. That's the next three terms. Next, negative 3, 6, negative 12, and 24. If we go positive and negative like this, there's no way we can add or subtract the same thing. If we want the negative alternating, it have to be multiplied. And this is multiplied by negative 2 every time. So multiply by negative 2, and negative 48. Multiply by negative 2, positive 96. And multiply by negative 2, 192 negative. Right, so that's the next three terms. The next one is a little bit less obvious. But what we see is, whatever the number is, it is the sum of the previous two. So 2 is 1 plus 1, 5 is 3 plus 2, 8 is 5 plus 3. And the next one will be 13, 5 plus 8, 13, 8 plus 13, 21, 13 and 21 is 34. So that's the next three terms of the sequence. So that is the recursion relation. So we go from this term to the next. Or if we have two terms, we go from this two terms to the next. So that is the way we define the recursion relation, or recurrence relation. Is the equation that expresses a sub n in terms of one or more of the previous term. And the sequence is called the solution of a recurrent relation if the term satisfies the recurrent relation. The initial condition is for which the sequence specifies the term where it starts. For example, we have the recurrent relation. The relation has two things. The first, the equation or the relation itself, and then next we have to start what is the n, the first one, and of course here we say the first one. So this is the initial condition, the initial values. Let's find that for 1, 2, 3, 4. Of course, if we start from 0, we have 0 minus 1 is negative 1. We don't want to write a subscript negative 1 in the sequence. Right. Right, so now we have A naught is 2. Now we want A1. If you put 1 in for n, we have A1 equal A of 1 minus 1 plus 3, which is A sub 0 plus 3. A naught is 2 plus 3 is 5. Now, for 2, I'm going to put 2 in for n. And we have A1 plus 3. A1 we just found, which is 5. So give us 8. A3, going to put 3 minus 1 plus 3. 3 minus 1 is 2 plus 3. So A plus 3 is 11. Right. Next, let's the sequence A and B sequence satisfy the following recurrence. We have A naught is equal to 3, A1 equal to 5. Now let's try that. So we have A naught and A1 already. Now the question asks for A2, A3, and A3. So this is the question earlier. So now we answer for A2 and A3. So if we want A2, I'm going to substitute 2 in for n. So 2 minus 1, so A1 minus A naught. A1 is 5, A naught is 3. That gives us 2. Now, if we want A3, we're going to substitute 3 in for n. And we have 3 minus 1, 3 minus 2. So that gives us A2 minus A1. Right, A2 is 2, A1 is 5, that's negative 3. Right, so the only answer is that. Right, next, the sequence we did earlier, this sequence have a special name for it. It's called the Fibonacci sequence, which define the initial condition of 0 and 1, and then recurrent relation is this. By the way, I just want to show you this real quick. If you want to do sequence on the calculator, this particular calculator, I mean that one, hit mode, go to sequence, so highlight the sequence, hit enter, right, then quick. When hit y equal 2, it will show this. So once again, mode to have function parametric polar sequence. When we sequence, this button will give us the n. So x, if it is in function, this button will give us x. If it is in parametric form, it will give us t. If it is in polar mode, hit this button, give us theta. If it is in sequence, hit this button, we have n. So the 4 variables here corresponding to the type of function we choose here. Right, now, so, of course, we can just type, for example, n square, like that, right? But if we want to write a recurrence relation like this, we can say an minus 1. So instead of a sub n, we type that as a function. So we have to say the little u of n minus 1. We cannot of n minus 1, so just do that. So instead of subscript, we type like that. And initial values, when the minimum of 0, initial values is equal to what? 2. And then we hit second table. Wait a minute, there's something off. Oh, sorry. Forgot the plus 3. Now, second table, we have 2, which is the first one, and then 5, 8, 11, and so on. So that's how we generate the sequence. Right, a little more complicated when we have 2 terms like this. By the way, the calculator will not do more than 3 terms. I don't think so. I haven't tried. Right, so this we have 3 and 5. We start from 0, right? Now we're just going to type u of n minus 1 minus u of n minus 2. Now, we start from 0, but this time we have 2 initial values, 3 and 5, but we actually have to enter 5, 3 backward like that. I don't know why it does like that, but you see we have 3, 5, and 2, and the next one will be -3, and so on. So remember, the initial condition, we have to type it backward. It's backward to me, at least. Right, so how do we do the Fibonacci sequence? We start from 0. Initial values is 0 and 1. Have to type that backward. And here, in the relation itself, it is the previous term plus a term before that. And then second graph. That is all of the term in the Fibonacci sequence. Right, so we use u sub n instead of a sub n. That's the only difference, right? Because in this calculator, it's difficult to enter the subscript. I mean, this calculator, yes, but the one before that, difficult to enter subscript. So they just enter that as a function. And so, there. All right, if we do this by hand, we have f of 0, f of 1. Now we do f of 2, meaning put 2 here and here. So f of 1 is 1 plus 0, 3 minus 1, 3 minus 2, f of 2 is 1, f of 1 is 1, is 2. Right, and then 4. Now we just add the previous 2. So be 3 and 5, add the previous 2, and f of 6, add the previous 2, so it's 8. Of course, we confirm that with this, with the calculator. Right, that's good. Right, and sometimes we have the closed formula. We'll talk about that in the next section, and actually in the later chapter of the book we'll discuss that. But for now, let's just say instead of recursion, that's some disadvantage because if we want f of the term at 100, we need the two terms before that. So we cannot just jump randomly into any term in the sequence. We need the previous term to find it, and that may be a problem. Right. We see that in the next part of the section. Right. Arithmetic sequence. Arithmetic sequence is a sequence at which each term after the first term is A1 differ from the preceding term by a constant. And that constant called the common difference, D. So you have A sub n minus A sub n minus 1 equal to D, and A sub n equal to n. So we plus that on the other side. So this is defined as the recurrent relation. And with that, of course, we need to know where start. So usually we know we start from A1 and then we plus D to it. Right? So we have to know where start, and then we can generate the rest. For example, if A1 is 6, what is going to be the first 4 terms? So we know the first term is 6. For the second term, going to put 2 in here for n. So that gives us A1 minus 2. A1 6 minus 2 is 4. Now put 3 in for n. So give us A2 minus 2. A2 is 4 minus 2 is 2. And A4, 4 minus 1. So A3 minus 2. So what we see is that starting from A1, we just keep subtracting 2 every time to get to the next. And the question is, what will be A of 100? Of course, if we keep doing that 5, 6, 7, A 100 is equal to A of 99 minus 2, right? But if we just doing that, that'll take quite a little bit of work. We have to go 4 or 5 counting all the way to 100. That's too much. Now think about this. Look at the number. For 1, we do not subtract any 2. If we have A of 2, there's 1 of the negative 2. There are 3, there's 1, there's 2 of negative 2. So we take 2 steps. So think about that. Let me write as the list of numbers. 6, 4, 2, 0. The next one would be negative 2. Now think about this. We take 1 step to get to the second term. We take 2 steps to get to the third term. Take 3 steps to go to the fourth term. So to get to 100 terms, we need to take 99 steps. Or it's always 1 less than that, right? So because of that, A of 100 is equal to A1, and we take 99 steps, and this step is a minus 2. So pretty much that. We start from 6 minus 198 minus 192. Right. So that's how we derive the formula. Oh, actually, now here we derive the formula. Okay. So derive, and just like we said here, derive forward. So meaning that we can say it A2 is equal to A1 plus a common difference. A3 is A2 plus a common difference. I'm going to use this formula. Now, if we can substitute this here, so we have A1 plus D plus another D, so A1 plus 2D. Now, A4, if we substitute this to that, A1 plus 2D plus another D, so A1 plus 3D. So in that case, notice that the parent here is always, there's 1D. There's always one less than that, right? So one less steps to get from first to that n plot. So with that, continue a sub n equal to, we start from the first one, take n minus 1 step to get to d. Right, so that. Now, so that is forward. For backward, we start from a sub n is a sub n minus 1 plus d. And a of n minus 1, we just keep recurring, is n minus 2 plus d, substituting n minus 1 plus another d. And then here we substitute 8 of n minus 3, which is a sub n minus, I'm sorry, yeah, n minus 3 plus so this is n 8 n minus 2 plus d. Now we substitute this into this one, will be n minus 3 plus d, substitute into this, that's the 2d here. Right, so to substitute that into this, and substitute this into a of n minus 2. So there's 2d here. So n minus 3 plus d plus 2d. So that is 8 of n minus 3 plus 3d. And if this pattern continue, we stop at a1 plus n minus 1d. Right. Bottom line is a sub n equal to a1 plus n minus 1d. So this is called the closed formula for the recurrent relation. I said we defined earlier a formula that replaces the recurrent relation, so we do not have to depend on getting from the first to the next term, right? So for example, if we just have this, we want to jump right to 100 term, just go ahead and put 100 term in for n. That's it. Right, now for the following arithmetic sequence, write the a term of this. Well, we have the formula, just start with that. We know the first term is 4, and we want 8. So that formula is terrible, terribly wrong. Should be a sub n, not n plus 1. Sorry. So a sub n. So if we want 8, we're going to put 18 for n. And common difference -3. So that gives us 4 plus 7 times -3. 4 minus 21. Minus 18. Right, next, write the sequence, the general term. The general term is a sub n. For this sequence, we don't know, of course we know, but we are not given directly the first term. So the first term here is going to be 3, and to get from this to the next, we're going to plus 4. So common difference is 4. So with that, we can say a sub n equal to a sub 1 plus n minus 1 times d. And then we have a sub n. The first term is 3, n minus 1, common difference of 4. So that is the formula for h of n. Now if we want 15, just put 15 in for n. Three plus 14 times 4. 14 times 4 is 56. And 56 plus 3 is 59. Right? So know the first term and how to get from the first to the next. Give us the rest of the sequence. Alright, the next one, we are not given the first term. We don't know the common difference either. So what can we do here? Well, so in that case, what we just do is, let's say we have the slot. This is 5, 6, 7, 8, be 9. Right. 1, 2, 3, 4, 5. We know the fifth term is 20. So 1, 2, 3, 4, 5, 6, 7, 8. Right. How do we find the rest? Well, in this case, from this we have to plus a difference to get to that term, plus another difference to get to that, another difference to get to that. So 20 plus 1, 2, 3 gives us back to 44. We can solve for solve for D. Give us 8. So meaning that we're going to plus 8 to get to the next term. If we want to plus 8, go to next term, we subtract. So that gives us 12. Subtract 4 to go backward. Minus 4. Minus 12. So we start with minus 12. So once we know where we start, we can just use this formula to find the n term. Now we want the 20th term. The first term we know is negative 12. N minus 1. 20 minus 1 times the common difference, 8. So negative 12 plus 19 times 8. It's 140. Right. So that is arithmetic sequence or arithmetic progression. Next we have a geometric progression. Geometric progression is just, instead of adding the same thing to the next one, we multiply the same thing to the next one. So we could say recurrence. This is geometric. We can say h of n is equal to the previous term times the common ratio. So the first term, a1, and r is common ratio, then the formula would be like this. So it's kind of like what we have earlier, in the sense that the ratio it is multiplied instead of, I'm talking about this one. It is multiply instead of add. It is multiply. It is power instead of multiply. Right. Of course, we can derive from this to that easily. So, for the following geometric sequence, if the first term is 3, the common ratio is negative 2. What is the 7th term? So we just said if we want to write that, we start from 3, and then the next one we multiply by negative 2. So negative 6, multiply by negative 2, 12, multiply by negative 2, 24, negative 2, 48, negative 96, 1, 92, 1, 2, 3, 4, 5, 6, 7. Right. Of course, we can also use the formula a sub n equal to a1 times r to the n minus 1. If we want the 7th term, we put 7 in for n, and we start from 3. The common ratio is negative 2 to the 8 minus 1. So 3 times 2, negative 2 to the 7. I'm sorry. Put 7 in for n. That is 6. Negative 2 to the 6 is 64 times 3, 192. So either way, we have that. Next, write the general term and use it to find h of 6 for this sequence. For this sequence, we know we start from the first term is 9, and to get from this to the next, we need to multiply by something to get from 9 to 3, and multiply the same thing from 3 to 1. So in that case, the ratio, if we multiply, so we say 9 times something is equal to 3, so r is equal to 3 over 9, which is 1 over 3. So 1 over 3. With that, we can put in the formula a sub n equal to a1 times r to the n minus 1. Start from the first term is 9. The ratio is 1 over 3 to the n minus 1. Right, of course we can stop there, but just review some properties of exponential exponents. 9 is 3 squared, right? This, we can say that power to the top, power to the bottom. 1 raised to any power is still 1. So pretty much we have 3 squared times 1 over 3 to the n minus 1. And finally, we multiply that on the top. If we want to divide two things, is subtract the exponent. So give us 3, 2 minus n plus 1 minus n plus 1. So that 2 and 1, so that 3 cubed. 3 to the 3 minus n. Of course, you can use any of that, but of course, you can just stop in that form. Right, so that is geometric sequence. Of course, there will be more details later chapter of the book. Next, we have the summation and summation notation. So we write the summation notation like this, meaning that we're going to add all the term by substitute the lower limit in here, and then add that increasing until we have the upper limit. I'm sure this is not the first time you see this summation notation. Right. And the index here, on the index of summation, usually in engineering we use j, because I is the index, is the imaginary number. We don't want to mess with that, so we try to use something else. To j, k, or m, n, anything like that. Right, now let's look at this. Expand and evaluate. So here we're just going to put 1 in for I. And 2 increase for that. Right, so just the index from 1 and just increase by 1 every time. So that gives us 2, 5, 10, 17, and 26. 60. Right. So we just substitute the index, the lower index, lower limit, and then increase by 1 until we see the upper limit. Right, you said. Then you may ask, can we use a calculator for this? And may I say yes. For this calculator, if you go to math, go down to option where it says summation, this one, and we just enter exactly as we see it. Oh, the reason is n, because I'll still have the calculator in the sequence mode. If it is in the function mode, when you hit this, it gives you x. Doesn't matter, because you can use any letter you want. I use n here just fine. We go from 1 to 5, and here we have n squared plus 1. Yeah, 60, right? So just that. This is just some basic notation for this. Of course, now we just substitute 4 in for k. Start from the lower limit. So I have that. Right? And of course you can do the math here, but I'm just going to put everything in the calculator here. Option 0, by the way, if you use this calculator. Alright, so we go from 4 to 7. So I have -2 to that -5. That's -100. Right. So just do that. Of course, we can use the product. The reason the summation use that letter, because this is the Greek letter, sigma, of course, equivalent to S in English. So that's for the sum. If we want the product, we use pi, which is equivalent to the P in English, which stands for product. Right. And the last problem I want to do is this one. So when we combine something like this with the infinite limit, upper limit, the index does not match. So we have to somehow match the index. And normally it matches the index. We also have to match the power of x. This problem kind of out blue, but if you take a different class, this might be useful. So what we do here is for this one, we're going to let this equal to k. And we get this equal to k. For two different deal here. If that is the case, so we have here k is equal to n minus 1. So that means n is equal to k plus 1. And n is equal to k minus 2. Right? We substitute that into this, substitute that into this. So this problem, let's say that is summation s. Instead of n, I have k plus 1. And then we have n, that k plus 1. C of k plus 1. And x, that is n minus 1, so that to the k. Then next, we plus 3 times n is k plus minus 2. C of k minus 2 and x to the k. Right, let's simplify. Subtract 1 on both sides, k equal to 0. Move the 2 on the other side, we start from 2. By the way, this one go to infinity, so there should not be any problem. Indefinitely missing a few terms doesn't matter if we start from 0 or start from 2. Doesn't really matter. Now the problem is we have x to the k, which is good. Now what's not good is this term start from 0, this start from 2. We cannot combine them. So in that case we have to split. By this we mean put 0 in for k, and put 1 in for k. And then the series will start from 2, right? Right, simplify this, give us just C1 x naught and 2 C2 x to the first, and this you can combine the series together. So this is the usual exercise. Just work with the index, but you can combine the summation like that. Will be useful in another class. Now with that, we finish section 2.4. As always, thank you for watching. See you in another video in Discrete Math.